So when we say the difference in electronegativity, we look at element number 1's En. So we could say 4.0 if we're dealing with fluorine. And element number 2's En. Let's say it was our 0.7. The difference there in those electronegativities is 3.3. So that's what we're looking at when we talk about electronegativity difference, is literally subtracting the two electronegativity values that we've got. If we have an electronegativity difference of 3.3, that is purely an ionic bond. One of those atoms loves the electrons enough to completely attract the electrons. The other atom doesn't care about them enough, it'll completely give them up. Now, if we have two elements that love electrons exactly the same amount, they have identical electronegativities. What's the difference in their electronegativities? 0. They have no difference in electronegativity. So if you have no difference in electronegativity, that is a purely 100% covalent bond. The only time that happens is when you have, guess what? What would cause 0 difference in electronegativity? Same atom. Hydrogen to hydrogen, oxygen to oxygen, nitrogen to nitrogen. So we're going to talk a lot more as we go along about the diatomic molecules. So those are our two extreme cases. A difference of 3.3, purely ionic, a difference of 0, purely covalent. If we have a difference of 1.7 or less, it's a covalent bond, but there's a continuum here. So if we go from 0.03 to 1.7, that's polar covalent. If we go from 0 to 0.3, that's non-polar covalent. So what is this idea of polar? Okay. Have you ever heard that you and somebody else were polar opposites? Maybe? Maybe a sibling, maybe a friend, maybe, man, I have a dear, wonderful, sweet friend, and she and I are polar opposites. Best friends, couldn't be more different. So when things are polar, they're pretty different, or we have poles, like the North Pole, the South Pole. They are as far from one another as you can get. If we have a polar covalent bond, they're not sharing the electrons evenly. They are sharing them. One of them attracts those electrons a little bit more closely. So what we end up with is a situation where we have partial charge. We don't have ions, but we have partial charges. If it's non-polar covalent, they are shared evenly, right down the middle, split 50-50. So if we look at polar covalent, water is a polar molecule, and the hydrogen don't love electrons as much as oxygen does. So what we get is this little region. Boy, that's a terrible picture. Have you ever seen water drawn as Mickey Mouse? Okay, we very often do this. There's oxygen. There are two hydrogens. That's water, Mickey Mouse. So what we find is that these little hydrogens don't love the electrons quite so much. And so oxygen is free to suck more of the electrons down around it. So what we end up with is, on this molecule, Mickey's ears have a little bit of a positive charge. They're not ions, but there's an area of charge. Mickey's chin has got more electrons around it. There's a region of partial negative charge. So that's a polar molecule. We've got something that's sharing electrons. It's not quite sharing them evenly. So water is one example of a polar molecule. Okay? And we'll talk a lot more as we go about polar and nonpolar. So here's this graphic should help you a little bit. If we go from all the way over at the side where it says nonpolar covalent, where the electronegativity difference is 0, those are nonpolar covalent. They're sharing evenly up to about 0.3. Starting at about 0.3, we start to see some ionic characteristics. Okay? As we go from 1.7 up, oops, sorry. So from here up, we say they're more ionic than they are covalent. So from that point up, we're going to call it an ionic bond. Okay? So let's do a quick quiz, okay? I'm going to turn off the video.